Any questions about anything from last time? About anything? The way the course is set up or anything? You might have noticed that I posted the lecture notes and the video of the lecture in the aftermath. So, especially that first lecture goes over a lot of things about the way the course is set up. If you ever need to consult that, it's there. Today's a momentous occasion. I'm going to talk about the Cauchy-Riemann equations, which is the first place you kind of notice that there's something different about calculus on the complex valued functions. Before I get rolling, I need to mention the topology of the complex plane is the same as the topology in R2 by the obvious association with xy with x plus iy. And then convenient notation is that the disk of radius r about z naught, we will write it like that, it's the open disk. And so in the complex plane, it's easy to describe as the point z such that z minus z naught in modulus is less than r, because the modulus is just the distance in R2 between those 2 points. And of course, that means that the topology in the complex plane is described by the open disks. Omega, a set in the complex plane, is open if for each point in z naught there's a radius that's positive, and of course that radius might depend on z naught. So if z naught's near the boundary, well then that would be a little tiny disk. And if z naught's well inside, it'd be a much bigger disk maybe. Anyway, there is an r bigger than 0, so that you can stick a disk, open disk, totally inside omega. That's the definition of openness. Okay, and so if I'm going to do calculus on the complex numbers, step 1 is to define what I mean by a limit. And it's a very straightforward, easy one. We'll say that the limit as z tends to z naught of f of z is equal to L, that's a complex number, means that given epsilon bigger than 0, there is a delta such that delta bigger than 0 such that the distance from f of z to L, that's the modulus, is less than epsilon when, this is kind of painful to write because it looks exactly like freshman calculus. So when z minus z naught is less than delta, and it's very important to say that z is not equal to the z naught. Because when we do differentiation, we'll have a difference quotient. And of course, we don't want to divide by 0 in the difference quotient. So that's an important part of the definition. Continuity would mean if it even held at the z naught spot. Anyway, this sure looks like freshman calculus. And in fact, it's an easy exercise to realize that. So pull out your freshman or any old calculus book, look at your real calculus book, change the x's to z's, and change the absolute value x to the modulus of z. And I didn't do all the things you should read in the book, like show that the triangle inequality holds for the modulus, but it does, which means all the inequalities and everything you ever did in freshman calculus is going to work exactly the same and look exactly the same. So that leads you to believe that, oh my God, this is kind of a tedious, routine thing to do, and for a while it is. So the basic fact is the basic rules of differentiation that you learn for real functions. So the basic rules and facts of R calculus goes over to C calculus about limits, difference quotients, etc. So an example would be, I haven't defined derivative yet, but when I do, the derivative of a product is going to be the product, the product rule, etc., and the quotient rule too, and in fact the chain rule. If you look at the right proof of the chain rule, for example, the one that's in Baby Rudin, that proof of the chain rule goes through perfectly for a complex version of the chain rule. Okay, so I'm not going to mess around proving all those things because it would be an exact repeat of the real version. Let's see, a little lemma we're going to need. Let's see, did I skip? I'm going to define differentiable in a second, so I should have done it before I wrote that formula there. But we'll need a little lemma, a very little lemma. And that is that the limit, let me write, I'll write complex function f of x plus iy is equal to u of xy. So the real part depends on x and y, and the imaginary part depends on, so it's a function of x and y. Okay, so that's a thing that maps C to C. And if you think about what the limit means as z tends to z naught, I'll also write z equals x plus iy, and z naught equals x naught plus iy naught. So let's see, limit of fz equals L is equivalent to the two things that the R2 limit as xy tends to xy, x naught, y naught of u of xy equals the real part of L. And the limit, let me see if I can do something. There's a virtue to having this thing here. Let's pick it. Control copper. Okay. So I'll change that to a V, and I'll change this to imaginary part. I don't know if I saved any time by doing that. Those two things. That's sort of an obvious limit. In fact, rather than give you a triangle inequality type proof, I'll give you a picture proof of that. So if I had z here and z naught here, and the distance, let's see, this distance here, oh no, it's not z naught, it's going to be L. Z and L. What am I doing? This is f of z. Okay, so that's, let's see, f of z. And so that red line is the distance. And here's a blue line and a green line. The blue line is absolute value of u of xy minus the real part of L. And the green line is the absolute value of v of xy minus L. And the red line is f of z minus L in length. Okay, so the fact that the legs of a triangle are less than or equal to hypotenuse does the implication to the right. And the fact that the hypotenuse is squared is the sum of the squares of those two things If both those go to 0, then of course that red one's going to go to 0. So that's all there is to it.
I think the L should be imaginary.
Imaginary part of L. Yeah. So it's just Pythagorean theorem, and legs of a triangle are less than or equal to the hypotenuse. Okay. Questions about anything so far? Let's see. Okay, so finally I'm going to define what Math 530 is all about. We say that f is complex differentiable. At a point, let's say A. That means that the limit as z tends to A of the difference quotient, f of z minus f of A over z minus A. This is a complex difference quotient, which I like to call dq, exists. And of course, if it does exist, we're going to call it f prime of A. Okay, and Math 530 is going to be about functions that are complex differentiable on an open set. Complex functions that are C differentiable on an open set. So it's got to be an open set. So there's always an open set in the background when you're talking about the functions we're going to study. There's a word for such functions. They're called analytic functions. That's a German word. Yeah, the French word is holomorphic. And funny that what the Stein in the beginning mentions that holomorphic is different than analytic, but there's a theorem that says they're exactly the same thing. So I'm not going to dwell on the difference of the meaning of the words. For me, they're going to be synonymous, and I'll explain very quickly why they're synonymous, because it's an if and only if kind of thing. But it's not obvious in the beginning. It's going to follow from our work on the Cauchy-Riemann equations in the next couple days. So, or you could call them holomorphic. For some reason, in several complex variables, holomorphic is the preferred word. Okay, so I guess standard at this moment to do an example. F of z equals z squared. It's very simple to show that it's analytic. In fact, it's analytic on the whole complex plane, and it's going to be complex differentiable on the whole complex plane. The difference quotient is z squared minus a squared over z minus a. You factor the numerator and cancel out the z minus a, and you get z plus a. And it's very routine to see that that tends to a plus a equals 2a, as z tends to a. Which is what you'd expect, and that's exactly the same as the freshman calculus example. So you think, oh, this is going to be a snap. Everything I write down is going to be complex differentiable if it has a formula. But the second example everybody shows you is that the function f of z equals z conjugate. Let's say I should write, let's write z equals x plus iy. Z conjugate is x minus iy. that's not complex differentiable. And let's see, there's various easy ways to see that. I think I want to do it in a geometric way. So here's some facts that I skip a whole bunch of facts in the beginning because you can read them in the book and they're very standard. But there's various facts about the modulus, for example. The modulus of a product is the product of the moduli. And same for quotient. The modulus of a quotient is what you would guess, just like absolute value. Of course, if w is unequal to 0. And other things to know is that the conjugate of z times w is the conjugate of z times the conjugate of w, etc. And same for quotient. The conjugate of the quotient is the quotient of the conjugates. Stuff like that. Easy to check. I'm going to use that in my calculation here in a second. Let's see. Last time I wrote down what I meant by e to the I theta is cosine theta plus I sine theta. And e to the minus I theta is, let's see, cosine of minus theta is cosine theta. And sine of minus theta is minus sine of theta. And so we see, for example, that e to the minus I theta is e to the I theta conjugate. And it's not hard to show that that's the same as 1 over e to the I theta. That's something to check. And that's the n equal minus 1 case in de Moivre's formula. Anyway, those are the facts I want to use in my next calculation. They're easy to check. Let's see. So now I can check that fact. Let's take the difference quotient for z, the z bar function. That would be z bar minus a bar over z minus a. And now I want to write that in polar form. That's going to make this obvious. Let's see. So I'll have a and a z. And I'm letting z slide into a. And I'll write this this complex number that represents that thing right there as r e to the I theta. So that's going to be equal to z minus a. So that's like a complex number. That's like a would be the origin, and that arrow represents the complex number z minus a, which in polar form I'll write r e to the I theta. Then, when I use that notation, I can write this difference quotient as r e to the I theta conjugate over r e to the I theta. The r's and let's see, that would be r e to the minus I theta over r e to the I theta. The r's cancel and I get e to the minus I theta times 1 over e to the I theta. And that's 1 over e, that's e to the minus I theta. That's the de Moivre formula. And so I get that this difference quotient is 2 e to the minus I theta. And that's supposed to be a complex number there as z slides into a.
Oh, wouldn't it be to the negative?
2 to the 2 power. Yeah, 2 minus 2. Minus 2I theta. So the fascinating thing here is that that's a different complex number no matter how you slide in. So here's A. I can slide in along different angles, and I get different values for that limit. If this complex derivative existed, they'd all have to be the same thing, the same complex number. So the thing that blows it is that we get different limits along the rays. Okay, and that's sort of a key feature of analytic complex differentiable functions. Those all have to be, they'd all have to be the same.
Is it just e to the negative 2 I think that is without the 2?
Yeah, I don't know what's going on. Thank you. Okay, so, and you know, if you look at that function, x minus iy, it's incredibly smooth. It's in the real part and the imaginary part are infinitely differentiable. So you think, oh, that's going to make it clearly complex differentiable. Not true. There's something special about being complex differentiable. Let's see, we're going to need a little theorem here to get out of the way. If a function is complex differentiable at A, it's continuous. So f C differentiable at A implies f is continuous at A. And the proof you learn in freshman calculus is the proof I'm going to do right now. So let's see. We know that the difference quotient, f of z minus f of a over z minus a, that's going to be, in the limit, that's going to be f prime of a. So that's equal, so that would be equal to that plus something small. So plus an error, e to the z, where e to the z tends to 0 as z tends to a. Okay. Now I'm going to solve for f of z here, and I'll get that f of z is equal to f of a plus f prime of a times z minus a. This should look familiar. It kind of looks like a first order Taylor series, plus e to the z times z minus a. Fascinating. That's complex linear. So being complex differentiable means that it's going to look like a complex linear thing plus something that goes to 0 rapidly, to order 2 in fact. So if I let z tends to a now, this, of course, this tends to f of a. This part, oh, remember the rules of all the rules you learned in freshman calculus hold for complex limits. So this one is going to be the limit of a constant times z minus a would be the constant times the limit of z minus a as z tends to a is a big fat 0. E to the z, I just said, goes to 0 as z tends to a, and so does z minus a again. So, and this is as z tends to a. So we see that the limit of f of z is f of a. An interesting thing from this calculation is that to be complex differentiable is going to imply that locally it looks like a complex linear thing plus something that goes to 0 faster than z minus a. Questions about that? That's straight out of freshman calculus book. Okay, now I can finally do something that feels new. The Cauchy-Riemann equations. Subject of the day. If f is complex differentiable, and I'll write my f now like I've been doing, f of x plus iy equals u of xy plus iv of xy is C differentiable at z naught, let's say, which is x naught plus I y naught. Then the first partial derivatives of u and v exist. Let's see, the first partials derivatives of u and v exist at x naught y naught, and they satisfy the Cauchy-Riemann equations. And see, the Cauchy-Riemann equations are du dx equals dv dy, and du dy equals minus dv dx. Two equations, two partial differential equations, and that's true at x naught y naught. Okay. Let's see, some standard notation that's going to make all the writing more efficient. Standard notation is that subscript du sub x means du dx, etc. I'll also use a shorthand notation that u super naught is u at x naught y naught. And dv dx super naught is dv dx at x naught y naught, etc. That'll make the writing go by more quickly. So I'm going to prove now this Cauchy-Riemann fact. Questions about anything so far? Well, let's see. That the z-bar example leads me to believe that I should be checking directions. And the interesting thing is, to get the Cauchy-Riemann equations, I only need to check two directions. So step one here is going to be let z slide into z naught along a horizontal line. So let's let z slide into z naught along the horizontal. Okay. So let's think about a picture here. There's a horizontal. Here's z naught. If I want to slide in horizontally, let's see, this would be z equals x plus I y naught. This would be x naught plus I y naught. So that x would be bigger than x naught, and I'm going to let it slide into z naught like that. That's the plan. So when I write the difference quotient and do exactly that, the difference quotient would be, let's see, I'll do it carefully this time, u of x y naught plus u of x naught y naught, minus rather. This is the real part. And I have the imaginary part, plus I times v of xy minus v of x naught y naught. And on the bottom, I'd have x plus I y naught minus x naught plus I y naught. And when you clean that up, you get u minus u naught over x minus x naught. The imaginary part cancels in the bottom. And then I get plus I times v minus v naught over x minus x naught. Oops, I gotta be careful. This is u of x y naught minus that, and this is v of x y naught minus that. And you'll notice that those are exactly the difference quotients for the first partial derivatives at x naught, y naught. So that baby lemma, the baby lemma, if the thing is complex differentiable, then those two real limits are going to exist. And it's an if and only if thing. So the baby lemma implies that the first partial derivatives exist. Let's see. The baby lemma. Let me move this. Is going to imply that this tends to the real part of the limit, and this one tends to the imaginary part of the limit. And because those limits exist, that means the first partials exist. So part of the theorem is we conclude that the first partials exist. At least those first partials. There's two more, and they'll be in the next one. And we have that f prime of z naught can be expressed as the first du dx at x naught, y naught plus I times dv dx at x naught, y naught. This is my own thing that I always do. I'm going to call this red box number 1. There's going to be a red box number 2, and when we equate them, we're going to get the Cauchy-Riemann equations. But I'm going to refer to these calculations many future times in the class. So the book doesn't mention red box number 1 and red box number 2, but I use these terms in the future. So that's step 1. Step 2 is to slide along the vertical. And let's think about that. Let's see, vertical. I'd have my z naught equals x naught plus y naught again. And this time I want to slide in along the vertical, so this would be z. X naught would be held steady, but the y now is the variable. And I'm going to let it slide in like that. And when I do the same old routine, I'll try to speed it up this time. My difference quotient would be stuff on the top. And on the bottom, I would have z would be x naught plus I y naught minus x naught plus iy plus x naught plus I y naught minus rather. Notice the x naughts cancel, and I get something on top. And on the bottom, it's going to be I times y minus y naught. Different. That's pretty different with that I there. And so I can pull that I out in front and get a minus 1 over I. Not a minus, but a 1 over I. And then you'll see that I get the difference quotient. This time it'll be x naught y minus u naught over y minus y naught. And plus I, I'll get a v of x naught y minus v naught over y minus y naught. and 1 over I is minus I. And if I multiply that minus I through there, let's see, I'll use a blue arrow. Let's see, I times I would be minus 1, and I have a minus, so this is going to go into the real part and be dv dy at x naught y naught. And then this one's going to be plus, this is, let's see, this, the other one, I'll use a green line for this one. What do I have? I have minus I in front of that. So this is going to be minus I times du dy. Okay. And so we get red box number 2. F prime of z naught. By the way, those first partials are going to exist because of the Bailey lemma. And now I know that this red box number 2 is v dy at x naught y naught minus I times du dy at x naught y naught. That's red box number 2. And when you equate red boxes, you get the Cauchy-Riemann equations. You equate the real and imaginary parts, of course. So equate the red boxes. Get the Cauchy-Riemann equations. Questions about that? That's a classic calculation. I guess Cauchy and Riemann both did it. Well, now that we have the Cauchy-Riemann equations, it's a simple matter to check. Z bar, the x would be, the u function would be x, and the y function would be minus y. U of xy equals just x. V of xy equals minus y. Very simple matter to see that the Cauchy-Riemann equations fail. One of them works, but the other one fails. They both have to work. So I showed you if it's complex differentiable, you get the Cauchy-Riemann equations. So if the Cauchy-Riemanns fail, the thing can't possibly be complex differentiable. So z bar is not C differentiable at any point. Okay, now another exciting example. The complex exponential function that I mentioned last time. E of x plus iy is e to the x cosine y plus I e to the x sine y. So there's the u and the v right there. And it's an easy matter to check that the Cauchy-Riemann equations hold. So, it's an obvious question to ask, is the exponential analytic? And the answer is yes, because there's a converse to the thing I just did above. I'll call it a partial converse because there's an annoying thing to think about. Partial converse to the Cauchy-Riemann equation thing. And the annoying thing between holomorphic and analytic is this assumption that I need a C1 smooth U and V. So let's see, whenever we're talking about analytic, we require an open set to be in the background. So the converse is, if U and V are C1 smooth, I'll remind you what that means in a second, on the open set omega, and I'm thinking of omega as an open set in R2, which is the same as an open set in R. But U and V are real valued functions of x and y. If they're C1 smooth on there and satisfy the Cauchy-Riemann equations, then f of x plus y, the usual thing here. I stick a u as the real part and v as the imaginary part, is complex differentiable. So it's analytic. That's going to mean that the complex exponential is analytic on the whole complex plane. And I want to make sure I want to be all ready to demonstrate this next hour. There's a calculus lemma we need to do this. Calculus lemma. I figure I ought to do it since it's easy. So let's suppose U is C1 smooth. That means U is continuous. First partials exist. And are continuous too. That's what C2 smooth would mean the second partials exist and are continuous in addition. Okay, so that's what we're assuming. And then the conclusion here is that I can expand U in a power series like thing. So that would be U of x naught y naught plus du dx at x naught y naught times x minus x naught. That's a times. Plus du dy at x naught y naught times y minus y naught. Plus an error. We'll call it a remainder. So this is just Taylor's theorem with remainder. But in the first order approximation, the remainder is simple to analyze. And we need it to go, it's going to go to 0, but we need it to go to 0 pretty fast. And it, being C1 means that the limit as xy tends to x naught y naught of that remainder term, it goes to 0 so fast that even if I divide by something that goes to 0, namely the distance between xy and x naught y naught, okay, so it goes to 0 much faster because I can divide by something that goes to 0, and it still goes to 0. Yeah, I guess I'll tell you a few words about the proof of this. And I posted the details, so what I'm going to say right now will help you read the details. Let's see, so here's u of xy minus u naught. I'm going to use a fundamental theorem of calculus here. So let's see, what's my function? I'll have, this is going to be x naught y naught. This is going to be xy. And then a spot moving along here is going to be x naught plus t times x minus y, x naught, and y naught plus t times y minus y naught. And t is going to go from 0 to 1, and that'll make that slide along like that. Okay? And this is going to be the I'm going to integrate from between 0 and 1, and this is the fundamental theorem of calculus. I take d by dt of this function u, I'll put it in red here. This is x naught plus t times x minus x naught, comma, y naught plus t times y minus y naught. And then I'll have here dt. So that's just a fundamental theorem of calculus. When t is 0, that's u naught. And when t is equal to 1, it's the other end, xy. Okay, so that's a very elementary calculus fact from the fundamental theorem of calculus. Then when I do the chain rule, I would see that this is equal to integral of du dx at the red stuff, which I can't stand to write, times x minus x naught when I do the chain rule, plus du dy at the red stuff, times x times y minus y naught dt. Okay, that's a nice thing to have right there. Okay, so that's a simple expression for that difference, and it's going to be easy to analyze. And the next step is now I want to subtract off the linear stuff. So now I subtract from both sides. Let's see what I'm going to subtract. Du dx naught times x minus x naught plus du dy naught times y minus y naught. Okay, I'm going to call that, think of that as a number, that's a real number, a. I want to combine that with that thing above. And it looks kind of similar to that, except there's no integral. So here's the integral. And the fascinating thing is that a is equal to the integral from 0 to 1 of a dt. Okay, so if I write it like that, then I get that u minus the first order Taylor approximation is something very, very simple to analyze. Namely, it's the integral from 0 to 1. I get du dx at the red stuff minus a constant, du dx naught, all times x minus x naught. And then the other one I would get du dy at the red stuff minus du dy naught times y minus y naught dt. That's my R thing. And that's very easy to analyze. It gets really small because it's C1. So that means this stuff right here is small. Because it's C1 smooth, so those are the things that are continuous. This will be small, or I can make it small. And then the rest of the stuff, when I integrate, it's just going to pop out x minus x naught and y minus y naught. So when I do, I've only got 10 seconds. I'll say see the web page. See the link on the home page for details.